Hello everyone and welcome to video number 4. Now that we've discussed moments and we have a general idea of how weight and balance affect the aircraft, I want to go over a few key terms that you're going to need going forward. We've discussed center of gravity previously. You may remember this problem from the previous video. We've described it as a balance point, but for this to become more real to you, I don't want this to just be a triangle on a piece of paper or something that you believe just because we tell you. So for that reason, I actually want to turn it over to Mark Rober for a sec, who gives a really awesome explanation about center of gravity.
Near impossible game, let me reiterate that as a carnival owner, the most lucrative games are those which the customers overestimate their chances of success. No game is a better example of that than the ladder climb. There's a subtle issue with this game that I think people realize but don't internalize the significance. The ladder converges to be supported on the wall at 1 point instead of 2. If it was attached at 2 points, it's like crawling across a rope bridge, which is pretty easy. Let's pretend this is you, and if you shrunk all the weight of your body down to the average location, we call that spot the center of mass, which we'll mark with this dot. And once again, we can double check this is the right spot because it balances perfectly on one finger. If you draw imaginary lines connecting the different support points, that creates an area, and as long as your center of mass dot is within that area, it's impossible to fall off. But as soon as your center of mass dot is even a little bit outside of the area of supports, you start to rotate and fall off. And this is true no matter which way you orient it. If you've ever bent over to pick something up, you actually know this fact, whether you realize it or not. In this case, the region of support is between the back of your heels and the tips of your toes. When you reach over, you will naturally move your butt back to keep your center of mass in between those support points. And if you don't believe me, try picking something up while standing against the wall so you can't move your butt back. At the very moment your center of mass gets beyond your toes, you start to tip over. In the case of the ladder game, you're only connected at 1 point, so even though it looks wide because of the ladder rungs, that area of support reduces down to a line. So if you don't keep your center of mass directly above that line, you will start to rotate and fall off. In other words, to win this game, you basically need to be able to crawl across a tightrope. And you might think, well, I can do a slack line, so I can do this. But a slack line is actually much easier for 2 reasons. You can flail your arms and legs out to adjust your center of mass to keep it directly above that line of support. And your center of mass is higher, increasing your mass moment of inertia, making you more stable. In the same way, it's easier to balance this umbrella when it's extended versus when it's collapsed.
So I'm going to pause right there. Again, I hope you gained something from me playing that video clip for you, but Mark Rober makes a very important point about the center of mass being a balance point and how you need to keep it within a certain range in order for it to function. We're going to be discussing center of gravity ranges later on in this unit. So again, this isn't just something that applies to airplanes, it applies to everyday life. It applies to carnival games and slack lines and even picking up basketballs. There's lots of things that this can be applied to, but of course, since we're aviation mechanics, we're going to be focusing on what's naturally applicable to us. So now that we have a better understanding of center of gravity and how that balance point comes into play, I want to talk a little bit about empty weight and empty weight center of gravity. So the empty weight of an aircraft is essentially all the installed operating equipment with a fixed location, things like the airframe, the power plant, hydraulic fluid. They have a term that they use that you'll get to know really well in next units called residual fuel and oil. And the idea of that is that when you go to weigh an aircraft, you have to empty out the tanks. However, there is some fuel that will remain in the lines, so they consider that part of the empty weight, even though it's not technically empty. And then they have fixed ballast. A ballast, which again you're going to learn more about later, is essentially a counterweight that they put in the airplane to help the airplane stay within that center of gravity range. And again, that center of gravity range, I think it really helps. The basketball analogy here really helps. So let me put that up for you real quick. Just as Mark Rober, when he was bending down to pick up a basketball, right here's probably good. Just as Mark Rober, how he had to bend his butt back in order to get his center of gravity, which is represented by this dot, inside of a range, in order to not fall over when he picked up the basketball. An aircraft has a range as well, and you have to keep the center of gravity inside of it by shifting weight just like he shifts his butt. So Again, I hope that helps get the concept to you, but bottom line, back to this empty weight of an aircraft, it's all the stuff that is off the aircraft when you go ahead and weigh it. So all the stuff that just stays on the aircraft when you have it completely empty, the fixed stuff. And you can find all this information and what the empty weight of an aircraft is in the flight manual. You also have the empty weight center of gravity. And the empty weight center of gravity, kind of obvious, is the center of gravity when the aircraft is at its empty weight. Now, that begs the question then, does center of gravity change? Like, is it different when it's heavy versus when it's empty? And the answer to that question is yes. When it's empty, it absolutely does change. And if you take a look over here, you can see a woman balancing a toothpick and a cork on her finger, and the center of gravity in that case is right here. But when you add weight to it, when you add the fork in, she's actually able to balance it on her finger because the center of gravity is on her finger. I'm going to show you a video of what this looks like in real life.
Tonight, at the dinner table, take a cork, take a toothpick, and insert this toothpick into the cork. Then, just for fun, try to balance it on the tip of your finger. I will impress you. It falls. I failed. Why? Because it is heavy here. Of course it falls. We never give up. I want to make it work. So I have an idea. I will insert a heavy fork into this cork. Don't stab your fingers, okay? Sounds like a terrible idea. I'm making it even heavier. But now, 3, 2, 1. Yeah, it works. Look at this. We balanced it. How?
So, again, the idea here that is super critical is that if you add weight, you change the center of gravity. If you add weight in certain places, that center of gravity can shift. And there's an acceptable range, just like I showed you in the Mark Rober video, of what a center of gravity can be on an aircraft, just like when Mark Rober was picking up the basketball. So, again, I hope these concepts help. Let's go ahead to reference datum in the datum line. So, a couple things worthy of note here. A reference datum is essentially some imaginary vertical line where all the horizontal measurements are taken from. So, like, for example, if you take a look over here at this diagram, you'll see that the datum in this particular aircraft is at the nose of the aircraft. And essentially, if you want to take a measurement from that, let's say that we have something. Well, how about I refer to this diagram to help out a little bit more. So if you take a look over here at this diagram, you're going to see the number 0 right here. And this number 0 is the datum on this particular aircraft. Datum can be different on all different kinds of aircraft. It's the manufacturer that decides it. So on this aircraft, it's the nose. On this helicopter, it's at the edge of its propellers. At this particular aircraft, it's the firewall, and at this particular helicopter, it's right in the center right here. So if you take a look back to here, let's say that our datum for this particular aircraft is right here along this yellow line where it says 0. If you have the front seat 37 inches from that datum right there, then you're at station 37. If your center of gravity is 40 inches from the datum, then your CG is at station 40. So really all the datum is some reference line that's put at some arbitrary place by a manufacturer that you can find in the type certificate data sheet. So again, I have that information available to you. Now let's go ahead and learn a little bit about negative and positive arms, weights, and moments. Move the face out of the way for a second. Okay, that's better. So if you take a look over here, you're going to notice that, again, we have our fulcrum right here on the aircraft, and when you put weight on the front of it, it wants to tilt forward, but when you put weight on the back of it, it wants to tilt backwards. Really, the location where you put the location of weight does matter. And for that reason, it's actually possible to have a positive or negative moment depending on where you put the weight. So just what they choose to do, if you have weight that is forward of the datum, and again, I'm saying datum, I'm saying this arbitrary line right here, not the center of gravity, that's different. If you have weight that is forward of the datum, and that is going to cause the tilt forward like you see right here, then the arm is negative. If you have something that is aft of that datum, if you have something that is back from that datum, like in this example, you have this weight that is back from that datum, that is going to be a positive arm. Again, let me restate that. The arm is negative when you have something forward of the datum, and the arm is positive when you have something aft or backward from the datum. Weight. So you can have positive and negative weight when you're doing moments as well. And it's as simple as this. The weight is negative if you're removing weight from an aircraft, like, for example, removing a ballast or removing suitcases. Weight is considered positive if you're adding weight to the aircraft, adding ballast, adding suitcases. And then moment, we know already from previously that moment is equal to weight times the arm. And that the sign of the moment is going to depend on the signs of the arm and weight. Because again, if you multiply a negative arm times a positive weight, your signs are going to turn out to be negative, because a negative times a positive is a negative. Well, let's say in that same example you have a positive arm and a positive weight. A positive times a positive is a positive. Or even a negative arm times a negative weight. A negative times a negative is also a positive. So the sign of the moment depends on the signs of the other two things. The sign of the arm depends on the location, and the sign of the weight depends on whether weight is removed or not. I hope this information is helpful to you. I've got a couple quiz questions for you to wrap it up with.